Okay, so I'm listening.
Yeah, so in the last lecture we proved the Euler theorem, right?
Yes.
Can you please repeat the proof, at least the last part of it?
The order?
Yes, the Euler theorem.
Yes, of course. Yes. The proof was very short. Okay. So okay, since it is a very basic term on the field of cryptography, it's very important to understand that. Okay, what is the order group? Okay, the order group is the all residue modulo n that are co-prime to n. Okay, for example, U6 contains only two elements, 1 and 5, that's all. Okay, because you want these elements to be invertible with respect to the multiplication modulo n, not addition, multiplication. So in U6, you have only 1 and 5. Of course, in UP, you have all numbers until P, I mean P minus 1, because they are all core prime. So what Euler says? Euler says that if you take a natural number A, okay, that is core prime to n, then A in the power of phi of n is 1 modulo n. And why is it true? Because if A is core prime to n, okay, now it doesn't matter if A is bigger or lower than n, because anyway, when we say A, okay, we refer to the residue modulo n, okay, because I mean, we are looking always in the world of modulo n. So here it can be greater than A, so what? Okay, okay, so if A is prime to n, so it means that its class of congruent belongs to un, or in other words, it means that this A is invertible with respect to multiplication. I mean, there is another B, or maybe A itself, such that A multiplied with B will be 1 modulo n. So it belongs to the Euler group. And we know by Lagrange, okay, that any element in a group, this is very general, any element in the group in the power of the order of the whole group must be E. Now, being E means being in the multiplication being remainder 1 modulo n. Okay, this is our E. I mean, this is a class if you want. I mean, if you refer to this one as an element, I mean, you can write it here like this. This is the class of all numbers that are 1 modulo n. So you take an element in the group in the power of the whole group order. So it must be E. Why is it true in Lagrange? Because any order of an element divides the order of the whole group. Okay, this is what we have seen before. Here, you see, G in the power of the model of the order of G is E. Why? Because this G can be written as the order of G multiplied with some Q. So this is E, and E in the power of Q is E. So this is a particular case in which our great G is the order group. Now, the order of UN is by definition this phi n.
Okay, thank you.
Okay, so today we want to see one of the fundamental theorems in modern algebra. Okay. By the way, this course is called in Bar-Ilan abstract algebra. Okay, so I know maybe it is a little difficult, but we are going to see examples that will, I hope, make things more clear. Okay. Now today we are going to see example of this isomorphism theorem, but it's one of the fundamental theorems. Okay, it is due to Emmy Noether, which is a great woman. I mean, she helped Albert Einstein. I mean, she also was a German Jewish. I mean, escaped from in the Second World War from Germany, going to the United States, and there she helped Einstein with his, I mean, in mathematics. Okay. By the way, she died early. I mean, for some medical issue. Okay. So this is our target today, and we are going to see examples. Okay, but let us start by recalling some basic notion. Okay. So definition. Let F from G to H be an homomorphism of groups. I recall that being homomorphism of groups means that it preserves the operation. I mean, f of x, y is fx, fy, okay, in the target. The kernel of f is, we denote it by this, all element in G going by F to the neutral element in H. Okay, you have seen this definition in the particular case of vector spaces, if you recall linear algebra. Okay, this is the kernel. I mean, if we can draw it like this. I mean, you have G and you have H, okay, and you have homomorphism F. Then the kernel takes, I mean, the kernel is all the things in G, or all the element in G that goes to E. Okay, so this is the kernel. And the image of F, you know what the image of F is. I mean, the image of F is all element in H that F which is no. Why does it do that? Okay. Okay. So this is the image. Okay, if you write it mathematically, this is all the elements in H such that there exists G in G such that f of G is equal to H. Okay, you know the things. Okay, so this is the image. So now we want to prove two things. Of course, if f is surjective, it means that the image equals to all H. Now we want to prove two things. We want to show that the kernel is always a normal subgroup in G, and the image is always a subgroup in H, but we cannot say it is normal because we don't have by F any control on H. I mean, H can be anything. Okay, it's not in invariant of F, but the kernel must be a normal subgroup. Okay, so let us prove that. I remind you, okay, recall that H is a normal subgroup of G if and only if to any H and G, okay, H in H and G in G, G, H, G minus 1 belongs to H. We have seen it in the on the end of last time, okay, because this means that GH always belong to HG. Now, this doesn't mean, okay, that G little h is equal to little hg. No, no. I mean, this is inequality of sets, which means that any element here appears also here and on the other direction, which means that if an element here is gh, so maybe you have another h here multiply with g that gives you the same element, okay? Okay. For example, we've seen that the SLN is a normal subgroup in GLN, okay? Okay, we are going to get back to these examples, but now I want to show you the following thing, okay? So we have claim. We claim that the kernel of F is a normal subgroup in G. Okay, so proof. So what do we have to show? First, we have to show that it is a subgroup. In order to show subgroup, we need three things. First, that it contains the neutral element in G. Second, that it is closed under multiplication. And the third thing is that if an element belongs to the kernel, so its inverse also belongs to the kernel. So let us go step by step. Of course, f of EG equals to EH, so EG belongs to the kernel. This is A. B. Okay. If X and Y belongs to the kernel, okay, so it means that Fx equals to Fy equals to EH. Okay, so Fxy, recall that is F is the homomorphism. It equals to Fx multiplied with Fy, but these both are 1. So also xy belongs. This means that curl F is closed under multiplication. Now see if X belongs to curl F, then F of its of course its inverse belongs to G. We want to show that this inverse belongs to H, to curl F. Okay. Okay. So, but we know that if F is homomorphism, we have shown that it is equals to this. So, but this is EH. This is equal to EH. So also X minus 1 belongs to the kernel. Because everything that goes to the neutral element, okay, belongs to the kernel by definition. Okay, so until now we have seen it is that it is a subgroup. For the normality, to any X in the kernel and so let us write the kernel by K, and let us write X in G. Okay, so we want to show that X, K, X minus 1 also belongs to the kernel. But of course it's true, because F of all these, since it is homomorphism, is equal to Fx. F, this is a little k. But this is E, because it belongs to the kernel. Okay, so, and these are reduced. I mean, this should not be E, because this is a general element of G, but they are being reduced one with itself. So it is AH. So x, k, x minus 1 also belong to the kernel. Okay, so we have finished our proof. It is also normal. Any kernel of homomorphism is a normal subgroup. Okay, this is the first claim. The second claim says that the image is a subgroup of the target H. Okay, why is it true? So let us go over the conditions. Okay, so of course, f of EG is EH because it is a general property of any homomorphism. So we see that EG, that we see that the image is not a trivial. I mean, it has it. I mean, the image contains the neutral. This is the first thing we should verify. The second thing we should verify, okay, is that it is closed under multiplication. Okay, so of course, if we have two elements in the image, what does it mean? It means that H1 is f of some G1, and H2 is f of some G2. Okay, so f of G1, G2, since f is homomorphism, it's f of G1 of G2. So f of G1 G2 is equal to H1 H2. Okay. So also G1 G2 belongs. So this also belongs to the image, because what is belonging to the image? That you have some source. So here, this is the source of H1 H2. So if H1 H2 belongs to the image, then also their multiplication, because this is the source that gives you H1 H2. Okay. So this is being closed under multiplication. And the last thing is to show that if H belongs to image of F, okay, so what is f of H minus 1? No, sorry. If H belongs to image F, it means that H equals to some Fg. Okay. So what is f of G minus 1? Since F is homomorphism, it's f of G minus 1. Okay, so what is the source? So it is H minus 1. Okay, so we have a source to H minus 1. This is the source of H minus 1. So it also belongs to image. Okay, so if we have an element, then also its inverse belongs to the image. So it's a subgroup. Let us see an example. Question: is there I would write does a homomorphism between Z3, I would say not homomorphism, monomorphism exists. This is the question. Can we find a homomorphism from Z3 to Z10? This is my question.
Ronnie, can I ask you something about the earlier proof?
Yes, of course.
Yeah, because I now thought about it, that we didn't show that the image of F is in A. We just showed that this is a group.
Sorry, I didn't hear you. Some disconnection. Repeat, please.
Yes, I'm saying that I don't think that we prove that the image of F is in H. I mean, we just proved that image of F is a subgroup.
No, of course it's in H. H is the target. I mean, we start by our H is. I mean, it is defined being the target of F. Okay. We only want to see that this is a subgroup.
Mm-hmm. Okay.
So it's closed under multiplication. If you take 2H here, the multiplication also will be here. And if you take an element here, so its inverse also will be here.
Yes, so it must be in H.
Yes. So can we find an monomorphism? Means that it is homomorphism which is injective. And the answer is no. Why no? Why not? Because let us write it F. Because what could be, okay? What is the order of image F? If it is injective, okay? If it is injective, so its image must be of order what? If it's injective, I mean, every element here goes to its own target here. So what could be the order of the image? Three. Okay, because any source has its target. Okay, but image F should be subgroup of Z10. And by Lagrange, three should have divide. I mean, any subgroup, its order divides the order of the greater group, which is false. So you cannot embed, it's called embedding. You cannot embed Z3 inside Z10. You cannot. Okay. Okay. Now, another thing we should have in mind is we also we have seen in linear algebra, but it was for the particular case of vector spaces. Now it is much more general. Okay, claim a homomorphism from G to H is injective, is mono. I mean injective if and only if its kernel is trivial. Remember, you have seen that in linear algebra? Or
Yeah,
it's too
I
old?
have.
Okay, okay. By the way, I mean, being homomorphism is exactly what we call then a linear transformation. You remember that we have asked then that FUV will be, I mean, TUV will be TU plus TV because the operation was plus, but it's the same thing in general as being homomorphism. Okay, so why is it true? By the way, if you prefer to have a stop, I mean, for 10 minutes and then get back to, I mean, you can tell me that. I mean, if you want to. Okay. Okay, proof. What is the proof? So one direction is trivial. I mean, of course, if F is mono, then in particular, the kernel of F must be only one element, and we have seen that EG goes to EH. Okay, so this direction is trivial. I mean, you cannot have two or more sources that takes you to EH. Okay, so it must be only this. But this the opposite direction is not so trivial, because you could think that okay, so maybe I mean, maybe if it's monomorphism, okay, then in particular it is true. But why it is sufficient to look at the pre-image of EG to deduce that in any point, okay, of the target, the pre-image will contain one element. You see what I mean? I mean, being monomorphism doesn't say that only the source of EG is unique. It says that any image, the source is unique. So why looking at this fiber, it's sufficient to deduce that it is true for all fibers anywhere. Do I understand what I'm saying? So this
Yeah.
is this is less trivial, okay? But it is only because f is monomorphism. For example, fx equals to x squared, okay? This is not a linear transformation, okay? So here, for example, the only source of 0 is 0, but the source of 9 is 3 and minus 3, okay? So here it's not sufficient to look at the fiber of the neutral element, okay? But if it was a monomorphism, if it was homomorphism, then it would be sufficient to look at this alone to deduce that f is monomorphism. So this is we want to show, okay? So, I mean, if the kernel is only EG, then to any x, y in G, if x, y minus 1 belongs to the kernel, then x must be equal to y. Because if the only element in the kernel is the trivial, so this must be the trivial. Or in other words, this means that x equals to y. Because the only way that this is trivial is when x equals to y. But then it means that to any x, y in G, f of x, y minus 1, I mean, being equal to EH, I mean, it's the same thing, but it's written in a different way. Okay, this is the same thing, this. Okay, it implies that x equals to y. Because this means that it belongs to the kernel. So x must be equal to y. Okay, but we know that this equals to fx multiplied with fy, and even also the minus 1 can be written here. Okay, and this is exactly the definition of being injective. I mean, if you have the same target, so it must be the same source. But this is only because f is homomorphism. Because if it wasn't an homomorphism, we couldn't write this from this. Okay, so from now on, if you want to check that homomorphism is monomorphism, it's sufficient to look at the kernel. I mean, if you see that the only element that goes to the trivial element is E, then you can be sure that it's the same thing at, I mean, everywhere, that you have only one source to any target, to any element in the image. Okay, so now we are ready. Maybe one last thing, because before we formulate the first isomorphism theorem, we write. By the way, I want to tell you that this course is is mandatory in the for computer science. Did you know that? I mean, okay. So because it has applications in computer science. Okay. So last claim. Okay, we say, I mean, it's not a claim. It's more okay, we can write it as okay. Definition, I would say. Definition. Let G be a group and K be a normal subgroup. Okay. We call the map from G to G modulo K. You remember what this is? This is, I mean, since it's normal, so it's not only the quotient set, it's a quotient group. The elements here are GK, little gk. These are cosets, these are shifts of K, okay? And this is, it has a group structure because it's normal. The group operation is, if you take two cosets, then GK, G1K with another G2K, it's G1, G2K, okay? So this is called the quotient group, okay? The quotient group. So the map is defined, I mean, we write it by ni, okay? So it is defined by, you take G to the coset GK. Okay, this is how we define this map. By the way, of course, this map in general is far from being injective, because if the kernel is not trivial, so any element in the kernel gives you the same image. You take some element in the kernel K, so little kk is K, of course. So in general, you lose information here. Okay, I mean, you cannot go back.
Can you show an example after the
Yes.
definition?
Yes.
Okay. Yeah, thanks.
Okay, for example, take G to be Z with plus. Okay, and take K to be 3Z. Okay, so you can take any element N here, goes to N plus 3Z, because the operation here is plus. Okay. So, by the way, of course, it is subjective. I mean, you can reach any coset here. Okay, because you can take any element of G. Okay. So this is the homomorphism from Z to Z3. Why Z3? Because the quotient of G by K are 0 plus 3Z, 1 plus 3Z, and 2 plus 3Z. Okay, for example, 4 is 1 plus 3Z. Okay. Of course, if you take knee of 6, so it is just the kernel. I mean, it doesn't do anything. Okay. But we are going to see more examples in the sequel. Okay. So this is this is called the quotient homomorphism. Why is it homomorphism? Why is it an homomorphism? Why is it a homomorphism? Okay. So it's very clear because knee of G1, G2, okay, is equal to G1, G2, K, okay, and it is equal to G1, K, G2, K. Why? Because this is as G2K, because it's a normal subgroup. So KG2 is like G2K. Okay, so this is the homomorphism. Of course, in the abelian case, any subgroup is normal. Okay, we're gonna see examples, okay, as time permits. So now we can formulate the first isomorphism theorem. This is due to Heminotter. And so, I mean, I always forget to write the he here. No. So she formulates not only the first, but the second and the third. And it's not only true to groups, but also to rings in general. So this is the very basic case. Okay. So what does she say? Okay. If phi from G to H is epimorphism, which means that's homomorphism, which is subjective, then there exists isomorphism from, we call it psi, from G modulo the kernel of phi to the same h. So we took an epimorphism and we have established an isomorphism. And when you think about it, it's very intuitive. Why? If we go back to our picture, okay, so here it is a subjective. Okay. Now, let us think about it as something smaller, okay? Because, I mean, if it's already isomorphism, then the kernel is trivial. So let us think about it as a smaller group, okay? So, of course, it's not mono. So, think of the pre-image of EH. We call it kernel. Now, when I say that G modulo this kernel, by saying that G modulo kernel is isomorphism to H, isomorphic to H, what do I mean? I mean that if you think of other targets here, for example, you take H here. So its source will be just a shift of this kernel. Maybe greater. Okay, so this will be some shift of the kernel. I mean, any pre-image of an element here will be a shift of the kernel. In other words, the images here correspond to shifts of the kernel. So by taking G modulo the kernel, you think of any circle here as a point. So you get an isomorphism. I mean, if you think as of any shift here as a point, then any circle goes to one target. So this is how you get isomorphism. Do you see what I mean? I mean, you don't have two circles that go to the same. So, but I mean, the fiber. What?
So just to be clear, there's isomorphisms between the equivalent classes in G. And
Exactly. Yes. Exactly. Yes. You see? Yes. So are you ready to the proof? I mean, it's not very long. Why doesn't it do that? Sometimes it does, sometimes it does not. Opa. Okay. So proof. And in the proof, we're going to recall some things that we have seen. Okay. So the note for brevity, we denote the kernel of phi by just k. Okay, so we have the quotient homomorphism that takes you from gk to no, sorry, we define the homomorphism. Okay, we define this map. How we define it? Okay, by psi of gk. Remember that elements here are shifts of k. This goes to phi of g. Now we want to see that this map first is well defined, and second, it is an isomorphism. What do I mean by saying it is well defined? I want to show that, I mean, here you take an element of G modulo K, but you use the data of little g. How do you know that taking another representative of the same shift results in the same image? I mean, you say that all this class goes to this image, but why you are so sure that it doesn't depend on the choice of the representative? So in other words, we want to show that all representatives in the same class have the same image. So it is well defined. Okay. Okay. Why it is well defined? Because if you have two representatives of the same coset, okay, so this is if and only if G2 minus 1 G1 K is equal to K. I just multiply both sides by G2 minus 1. Recall that this is a set equal to a set. So I multiplied both sets by G2 minus 1. So this means that this must be equal to K. Because if it wasn't belongs to K, then it wouldn't be the trivial shift. Okay. In other words, it means what is K? K is the kernel. That phi of G2 minus 1 G1 is E of EH. This is what it means to belong to K. But phi is homomorphism. Phi is homomorphism. So it's like saying that phi of GT of G2 is equal to phi of G1. Okay, because this is like saying phi of G2 minus 1, phi of G1 is equal, to EH, because this is the same thing as this one. And now this means that phi G2 is equal to phi G1. So it is well defined. It is well defined. I mean, it doesn't depend on the choice of the representative. You can take any representative, it will be the same image. So all the class goes together to the same target. Now we want to show that this phi is an homomorphism. Why is it a homomorphism? Okay, let us check that phi is homomorphism. Not only phi, but psi, okay? Why psi is homomorphism? Because psi of G1k, sorry, G2k is of course psi of G1, G2k, because k is normal, which is equal to phi of G1, G2. This is how do we define this homomorphism. And since phi is homomorphism, this is known, this is given, equal to phi G U1. Okay, so this is so psi is also homomorphism. Now we want to show that psi is iso. So for being subjective, it is sufficient to check the kernel is trivial. What is the kernel of psi? The kernel of psi is all the shifts of k such that phi of G is the trivial element in the target. But what are these G? These exactly the elements that belong to K. Now this is the trivial element in the quotient. So psi is mono. We call that G modulo K is a group, and the neutral element in the group is the all trivial shift. Okay, let me calm you, okay? Things are going to be later more practical, okay? But we have to pass through this. I mean, maybe this is the most difficult part in the course, okay? This is very abstract, but I think that if we go, if you are going back on it, you will see that it's not so difficult. Okay, so the psi is mono. Why it is subjective? Of course, it is subjective. Because to any element of H, I mean, we know it is given that phi is surjective. So to any element H in the target, there exists some G such that phi of G is equal to H. And so psi of gk will equal, which is phi g, will equal to h. So this is the source of any h, okay, in the quotient group. So this is surjective, injective, and homomorphism, and well defined. So this is an isomorphism. Okay, now it's 607. We want in the time that is left, okay, to see examples. Okay, examples. So if we've seen, we can take f from z to zn. Zn is z modulo n z. Okay, this is the shifts of nz. You have n such shifts. Okay, this is the exactly the zn. I mean, okay, because you can shift nz by 0, by 1, by 2 until n minus 1. Okay, so what is the f here? You take an integral element and it goes to m plus nz to this coset. So what will be the kernel? What will be the kernel of this f? Of course, it's epi. What will be the kernel, the kernel of this f? I'm waiting for you to tell me what will be the kernel of this f.
0 now.
Sorry?
0.
What will be the I mean, this is much bigger than this. This is only n elements. This is infinitely many. So the kernel cannot be one element, okay? What will be the kernel of this homomorphism? Remember that the trivial element here is nz, is the trivial shift of nz. So what will be the kernel of this homomorphism? It will be nz. Because if you take some multiplication of n, then it will be 0 plus nz, okay? So by the first isomorphism, I mean, this is nothing new, okay? If you take z modulo the kernel, you just get isomorphism with the target, which is nothing new because this is how we defined it, okay? So maybe we should have deleted, okay, and understand it now. So I repeat, the all group modulo its kernel is isomorphic to the image. So this was first example, which is some kind of trivial. Let us see another example. Think of f of this epimorphism from GLN R to R without 0. Okay, determinant determinant of a matrix. What is the kernel here? The kernel is all the elements that goes by the homomorphism to what is the, I mean, the operation here is multiplication. Okay, what is the kernel of this homomorphism?
All the matrices that have determinant of 1.
Yes, exactly. How did we call it? How did we call it? SLN. Remember, these all matrices with determinant 1. Now, according to this theorem, if we take GLN modulo this kernel, by the way, this is another way to show that SLN is a normal subgroup, because always the kernel, as we have seen that, always the kernel of any homomorphism is a normal subgroup. Remember that last time we have showed that, but this is another way to see it directly. If you have a homomorphism and this turns out to be the kernel, so it must be a normal subgroup. So the whole group modulo its kernel is homomorphic to R star. How? You take some coset here to its to what?
Shift of
What all matrices here have in common?
the determinant is
Okay, so it goes to here to what? Think of the original homomorphism. I mean, you remember what Eminator said? Okay, you take the shift of the kernel to the image of the of the initial homomorphism of G. Okay, so what will be here? It goes to what?
to G.
Sorry, what?
To G.
To K?
G.
No.
Identity matrix?
Sorry?
Identity matrix?
No. This, I mean, okay, we have started by the homomorphism, which is determinant. You take a matrix here, and it goes to its determinant. Okay, now we take the whole group modulo the kernel. So it contains shifts of the kernel. This is one shift. Okay, so what will be the image here? Think that this is our phi. We have denoted by phi in the theorem. Okay, so we said that any shift here goes to phi of the representative. So it goes to that G. Okay? Because you take the shift to the image of the original homomorphism of one representative. It doesn't depend on the choice of the representative. I mean, any matrix here has the same determinant, because here these all are determinant 1. Okay, so this is another example of this theorem. Okay, so let us, if Another example. Take this T to be the unit circle in the complex plan. I mean, all complex number with modulo 1, okay? This is what we draw by the circle. Okay? So this is our T. And take all, I mean, in other words, we can write it as cis theta, where theta can be anything. Because any complex number is R cis theta, but R here is 1. So you are left only with the cis theta, okay? I mean, here is an element, this is theta. So all points here are cis of some theta. Theta is the angle, okay? So now I want to refer to this epimorphism from R to T. Okay, this is, I call it phi. Okay, that takes any theta to cis theta. And I'm asking you, what is the kernel? First, of course, it is homomorphism. Okay. Why it is homomorphism? Because phi of theta 1 here is with respect to plus. Okay, so maybe it should be written. Because if it was with respect to multiplication, we had to take here a star without the 0. So now we are looking at this group, this additive group. Okay, so of course, theta of phi of theta 1 plus theta 2 is by definition cis of theta 1 plus theta 2, and we know it is equal to cis theta 1 multiplied with cis theta 2. Why? Because this is moving against the clock direction by the angle of theta 1, and this is another angle which is added. You know that from complex algebra? So this is homomorphism. And what is the kernel of this phi? What is the kernel of this phi? Okay. What are the elements in R that gets to 1 here? In other words, what are the angles that their cis is 1? This is the neutral element here in T, because T is with respect to multiplication. So what will be the kernel of this phi? I mean, what will be the theta?
All the z times pi z.
2 pi, 2 pi z.
Right.
Okay. Now, let me a little change now these things, because for now we see that R modulo 2 pi z is isomorphic to the target T. But I want to show it in a nicer way, okay? So instead of writing this, let me change a little. Okay, let me write it in this way. So of course, everything remains true. And now I'm asking you, what is the kernel now? I've changed it a little. I took theta to cis 2 pi theta. So what will be the kernel now?
Now it is only Z.
Yes, exactly. So by the first isomorphism theorem, what we can deduce that R modulo Z is isomorphic to the circle unit. Why is it true? Because we took the whole group modulo the kernel. It doesn't want. Sometimes he wants, sometimes does not. Okay. We have the time to last example.
Ronnie, I have a question.
Yes, of
What
course.
does it actually mean in in the practical approach? What does it mean that the R modulo Z is?
I explained. This is R. So this is R. Okay? This is R. What does it mean, R modulo Z? It means that you take this is R modulo Z. Okay? Because, I mean, you take the remainders modulo integers. Okay? But it's not exactly this interval. It's this interval when one is identified with 0, because both are integrals. So if you glue this one in 0, you get exactly the circle. I mean, all elements here corresponds to element here. This is what it means. That R modulo the integers, it's the element here, but when one is identified with 0, so it's exactly the unit circle.
But what does it mean that one is identified with 0?
Because here, okay, 1 and 0 are the same, because this is modulo integers. So 0 plus Z is like 1 plus Z. It's the same thing, because 1 plus Z is Z.
Okay.
But half plus Z is a point here. okay, which correspond to pi here.
Okay.
So in algebra, when we say this, you say circle unit. Okay, we have 3 minutes. Think of G as R2, okay, and we want to show, okay, think of H as this line. Okay, this is a line which pass through the origin, something like this. This is H. Of course, H is a normal subgroup in G. Why is it subgroup? First, because it's closed. You know that any solution to homogeneous system, okay, is closed. I mean, you take two solutions here. Their sum will be another element here, and also the product with the scalar. I mean, this is closed. Of course, any inverse is minus this point. So this is a subgroup, and since it's abelian, I mean, what is the operation here? Is to sum vectors. So of course it's normal subgroup. Now I want to show that G modulo H is isomorphic to what? To R. Because this is two-dimensional, well, this is one-dimensional, though, so this is isomorphic to R. How do I show that? How do we show this isomorphism, that there exists such an isomorphism? So the method is as following. You just have to define some phi from our R2 to R, okay, such that the kernel of phi will be exactly H. And then this is the first isomorphism. So what do you think? Phi of x, y, what will be? It has to be one-dimensional here because it belongs to R. What will be the target? What will be the image such that the kernel of this phi will be our H? What do you think? Tell me that, and we have finished this lecture for today. Okay. What can be the image of this two-dimensional vector? It should be a scalar, okay, because it's one-dimensional. But what will be the image such that the kernel will be exactly this H? I mean, that such that the xy that goes to 0 will be exactly this H. What do you think? And then we can apply the first isomorphism theorem to deduce this. What could be our epimorphism? So the epimorphism will be y minus 2x okay? The kernel of this phi is H. So our R2 modulo the kernel will be R. And what does it mean? It means that what is G modulo H? It's shifts of this line. So you can cover all the plane by shifts of this H. Okay? Okay. I'm feeling that we have to practice this. So I will let Tomer have some exercise. Don't worry, okay? We will understand it eventually. Okay. Anyway, I mean the speed depends on you. If you want me to stop and show more examples, I will show more examples, okay, of this thing. But the basic notion is that G modulo the kernel is isomorphic to the image. Okay, this is the first isomorphism theorem. Let me just show you this woman. Okay, you haven't heard about. I mean, she didn't want to get into this. I mean, she said, okay, I'm a woman. Don't think that it's like today, okay? In era period, I mean, women could not be a lecturer and etc. in the university. It was David Hilbert that told everyone, let her, she's a genius, okay? So it's due to him, to David Hilbert, that she got to what she got. Why doesn't he let me write Emmy? Okay. You see now my Wikipedia?
Yeah.
Okay. So can you can read about her? Okay. She died at age of
40.
yes, 53.
No, 53, right?
Yes. She died as a single. I mean, just because some medical problem. I mean, okay. But you can read about her. Okay. This is Emmy Noether. Okay. Thank you for listening. We are going to see more examples. Okay. In the forthcoming lectures. Thank you.
Thanks.
You.
Bye.
Thank you.